Hello everyone, welcome back to my last video in 2024. This is AP Physics 1 Unit 2 and they will cover 3 problems to help you review for the concepts. So the first one, it's on incline problem. For an incline which is 36 degrees from horizontal, that has a 5 kilogram object on it. Assume that object is not sliding, find the coefficient of static friction. When the object starts to slide, assume that kinetic friction is 0.2, find the acceleration of the object. So in this problem, the first step, we should draw a diagram of what it's saying. 36 degrees from horizontal, and it's an incline. So it looks like this. And the dotted line is the horizontal. Has a 5 kilogram object on it. So it's like this. And what we're trying to solve is the coefficient of static friction and the acceleration of the object. So A is equal to question mark, is equal to question mark, and mu K is equal to 0.2, and M is equal to 5 kilogram. Okay, so the first step when we solving the problem, draw a free body diagram, FBD. Let's analyze what's happening to this object. There's always a force of gravity down. There is a force of normal that's perpendicular to the surface, that when the object is contacting a surface, it always have a normal force. So it looks like this. Force of normal is saying that it has a static friction. It's not moving. So it must have a static friction. Something like this. Force of normal. Force of static friction. And they're all vectors. So here's the free body diagram. What we want to do is break forces into components. In this case, we can't just do straight x and y axis. That would be very complicated. So what we're gonna do here is to the x direction is the parallel to the surface, and the y component is perpendicular to the surface. And based on the force in the x direction, of course, there's a force of gravity times sine theta. The force of gravity times sine theta is the force if you break this into components. Then it has 2 components here. This is theta. That's the same theta as 36 degree theta. And this is sine theta. Fg sine theta. Minus force of static friction, which is equal to 0. It says the object is not sliding, so it must be 0. The y direction is equal to upward is positive, so we will say that force of normal minus force of gravity cosine theta is equal to 0. It's not sliding. Also, make sure to mention your axis, so we can say that downward is positive and the upward is positive. Now we can solve using these. Say that Fg sine theta must be equal to force of static friction. Got mg sine theta is equal to mu s times Fn. We don't know Fn here. Well, we do know that Fn appears in the y direction, so let's calculate in the y direction. Fn is equal to Fg cosine theta. So you can say that Fn equal to mg cosine theta. Now we can substitute Fn here. Mg sine theta, which is equal to mu s mg cosine theta. See, mg cancel out, the weight cancel out. We can divide by cosine by both sides, so we leave with mu s equal to sine theta over cosine theta. And if you took trigonometry, remember that this is equal to tangent theta. So mu s is only dependent on the angle of incline in this problem, which is tangent theta. And our degree is 36 degrees, so mu s is equal to tangent of 36 degrees, which is approximately equal to 0.73. And now, the object sliding. Let's solve for the components then. The forces in the x direction is the same, besides its kinetic friction. So it's Fg sine theta minus force of kinetic friction, which is equal to mass times acceleration. The y direction is not accelerating, so we can say that force in the y direction is equal to force of normal minus force of gravity cosine theta is equal to 0. And now, let's solve for it. So we got force of kinetic friction is equal. Actually, let's solve for A. A is equal to mg sine theta minus mu k Fn over m. Note that we just skip some steps, but Fg equal to mg and force of friction equal to mu times Fn. Now we are missing Fn. We don't know what Fn is. We can use the direction in the y direction to solve it. For normal equal to mg cosine theta. So we can substitute to our original equation. We got A is equal to mg sine theta minus mu k times mg cosine theta over m, which m cancel out, so A is equal to g sine theta minus mu k g cosine theta, which we can substitute value, which is 10 meter per second squared times sine of 36 degrees minus 0.2 times 10 meter per second squared times cosine of 36 degrees, which is approximately equal to 4.26 meter per second squared. Now let's look at problem 2. Assume pulley is frictionless, rope is ideal strain, and mu k is equal to 0.15. Like 5 kilogram one is M1, and 3 kilogram one is M2. So this one's M1, M1, this one's M2. So for the acceleration of the block when the blocks start at rest and blocks are in motion. So in this problem, we should do first is to draw the free body diagram. So FBD. For the mass 1, it has a force of gravity. It has a force of normal, perpendicular to the surface. It has a force of tension because it's a rope. There's tension. And if we assume that the object go this way is positive, then we will say that the friction is going this way towards friction. This is mass 1. For the mass 2, experiences two forces, force of gravity and force of tension. It's going down, so force of gravity must be greater. 2, 1. We see that the magnitude of the arrows matter, so Fg2 is less than Fg1. And it has a tension force acting on it. Force tension. Okay, let's sum the forces. So the force of mass 1 in the x direction is equal to force of tension minus force of gravity 1 times sine theta, which is equal to m1a. The sum of force of mass 1 in the y direction is equal to first normal minus force of gravity 1 cosine theta, which is equal to 0. And sum of the forces for object 2. It only has y direction force, but we are still writing the y here, which is equal to Fg2 minus Ft, which is equal to m2a. Note that the a in the first one and the third one are the same because it's an ideal rope where it's not structurable. Okay, so right now we can do here is that for the second equation we can solve for Fn is equal to mg cosine theta. And now what we're gonna do, we want to cancel out Ft. How we do it? We add the first and third equation, which the Ft has opposite sign, which when we add them, it cancels out. So let's do it. So, let's see. Fg2 minus Fg1 sine theta. Oh, for the first one, it has a force of friction minus Ff is equal to m1a minus force of friction is equal to m1 plus m2a. Now we can expand this, so that's m2g minus Fg1, so that's m1g sine theta minus mu k times m1g cosine theta. We solve for Fn already here, so you can just substitute that in, which is equal to m1 plus m2 times a. Now we can solve for a. A is equal to let's see, actually let's factor out a g here. G times m2 minus m1 sine theta minus mu k Fn, mu k m1 cosine theta over m1 plus m2, which we can substitute value in. That's equal to 10 times 3 minus 5 sine of 37 degrees minus 0.15 times 5 times cosine 37 degrees over 3 plus 5, which is, let's see, actually it should be 5 plus 3. 5 plus 3, which is equal to, let's see, approximately equal to negative 0.76 meter per second squared. We got negative sign, which means that this object will actually go down to the incline. So now we have to solve when the object goes down. Let's draw the free body diagram again. FPD. For the mass 1, it has a force of gravity. FG1, it has a force of normal. And it has a force of tension. But this time, the force of friction changes direction because how the velocity vector changes direction. So let's draw it here. Force of friction. And for the second one, it's the exact same. Besides, the force of gravity vector will be less than the force of tension vector. Now we can sum the forces. So F1 in the x direction is equal to, now we're going to assume that downward is positive. So this way is positive, and going upward is positive. This way going up is positive, and down is negative. In the x direction, there's a FG1 sine theta minus FF minus FT, which is equal to M1A. In the y direction, y is equal to Fn minus Fg1 cosine theta, which is equal to 0. Some force in the second object in the y direction equal to force of tension minus force of gravity 2. Now let's solve for the Fn. Fn is equal to m1g cosine theta. Is the second equation. Now we can add the first and third equation, which give you Fg1 sine theta minus Fg2 minus Ff, which is equal to, oh, for the third one, you should add m2a equal to m1 plus m2a, which we can expand this again. M1g sine theta minus M2g minus mu k M1g cosine theta, which equal to, actually, let's solve for A, divided by M1 plus M2, which that's equal to C. That's 10. No, that's 5. That's 5 times 10 times sine of 37 degrees. Minus 3 times 10 minus 0.15 times 5 times 10 times cosine 37 degrees, and all divided by 5 plus 3. That's approximately equal to negative 0.74 meter per second squared. Well, this is weird, because when we assume the object goes up, m1 goes up, the acceleration is negative, which means the object should go down. When we assume the object go down, the acceleration is actually going up. So this is a really special case. It's called damped motion, where it oscillates back and forth, but decrease in magnitude. The velocity magnitude and the acceleration magnitude, which will eventually the object will go to rest. But here's why. the force of gravity in the x direction, which is 5 times sine 37 degrees, is approximately equal to 3.009 newtons. What this means is that the maximum friction force to not having oscillation is 0.009 Newton. But in this case, the force of friction is way over this small value, which means that it will oscillate back and forth. Remember, the force of friction, it changes the direction when you change the assuming moving direction. So this force of friction, it always changing the magnitude of the velocity, which result in this damped motion. However, friction force is a dissipative force, means the energy is lost. Well, you can't say it's lost, but it's converted to the other forms. And the energy will eventually run out, which will result in the object in rest, and we will cover it more in Unit 3. But the next example is on circular motion and the Kepler's third law. What we want to do is we want to derive this equation using circular path. Well, let's analyze the force acting on the object. So some force in the in direction is equal to force of gravity, which is equal to MAC. Force of centripetal acceleration is what causes its moving in a circular path. And the only force we assume is only having a gravitational force. It's not affected by the other planets unless it's specifically mentioned. So we can say is that G times mass of satellite times mass of the primary over R squared is equal to MAC, mass of satellite, times velocity squared over R. We see ms cancel out, and the R cancel out. So if V squared equal to G MP over R. Now, we note above that speed is equal to distance over time, which in one revolution is 2 pi r over t. So we can say that G MP over R is equal to 4 pi squared R squared over T squared. Now we can isolate T squared here. That is equal to, let's see, T squared equal to 4 pi squared, and R moved to, so it becomes third R over G times mass of the primary. And this is Kepler's third law. And we can derive it using the circular motion. And this concludes my last video for 2024, which is the review video on Unit 2, the problems. And please like and subscribe, and we'll see you next time.